All right. In this video, we're going to be looking at the different types of discontinuities. This is kind of a word that we've been throwing around in a lot of the last videos, and so, it's apparent to me that some of you may not be exactly familiar with what discontinuities are. This is something that you probably may have covered in your pre-calculus classes or in your algebra classes. So in that case, this should be a helpful review because again, discontinuities are very important to understanding calculus. But if this is your first time hearing this word or are not familiar with this concept, then again, you're in the right place. So we're going to be looking at three main types of discontinuities. There are three main types of discontinuities, but before we get to that, what exactly is a discontinuity? So a discontinuity, if you want to explain it in a super simple way, is if we say we have a graph like this, right? And if I'm able to draw, so this, these are our axes, this is the actual graph. So if we're able to then draw a graph like this, for example, if I'm able to draw this graph without lifting up my pen, right? This is something that I can continuously draw without picking my pen up. On the other hand, if I had a different function, one that is not continuous, right? For example, if there was something like an asymptote, then I would have to, if I draw this, I would have to pick up my pen, move over here, and continue drawing. So in this case, this is a non-continuous. This is an example of the discontinuity. You can tell if a function is continuous or not. Again, if we're putting it simply, in a non-mathematical way, if you're able to draw the graph of that function without picking it up. So any of our, sine curves or any other loops that we can draw around on a graph, all of these are discontinuous because we're able to draw it without lifting up our pencil. So now looking at the three main types of discontinuities that you should be familiar with, these types of discontinuities. The first one we're going to look at is going to be a hole. And a hole is actually a discontinuity that we call removable. It is a removable discontinuity. So the first type of discontinuity that we'll be looking at is a hole. And this is one that is removable. So what does that mean? What is a hole and why is it removable? So let's say we have a function looking something like this. So if we draw the curve and then we have a hole and then the function continues. So a function like this is a discontinuous function. Specifically, it's of the type, well, the first type here, it's a hole. And you can see again, the whole function is continuous except at this point where we have a hole. And this is called a removable discontinuity because we can simply remove this discontinuity by filling in this hole. If we simply fill up the hole, we now have a continuous function. And you can see that this is not going to be possible with some of your other types of discontinuities. An example of which is a vertical asymptote. So if we have an asymptote like this is going to be vertical. Add a vertical asymptote. This is a non-removable or unremovable. What's the word? Unremovable, non-removable. Yeah, I think it's a non-removable. So a non. My pen seems to be giving me some difficulty. A non-removable discontinuity. And again, we can see this with looking at a quick graph. Is if we draw a graph here, for example, or here, let's do this. You only need one quadrant for this. We don't need to make it more complex. So if we had a graph, and here again we have some sort of vertical asymptote. This is again the example that I gave earlier. If we have an asymptote like this, a vertical asymptote, there's nothing we can do. We can't just fill in a dot or a hole somewhere and this suddenly becomes continuous. No, there's no way to remove this discontinuity. So a discontinuity due to a vertical asymptote is non-removable. Non-removable. All right. Hopefully this is making some sense. This isn't something that should be, super complex to understand. And now the third type of discontinuity, this is one that we see frequently with piecewise functions. And this is going to be a jump discontinuity. a jump discontinuity. And a jump discontinuity is another type of non-removable discontinuity. Non-removable. So if we look at an example of one of these jump discontinuities, we can see again, drawing out this quadrant here, we can have, for example, something that looks a little like this. We have a graph going, for example, here, and then upriver here. It continues, for example. Something like this. You can see we have a graph that is continuous. Then we have a jump, and it continues on at another point. So this is another type of discontinuity that we can't simply fix with a hole, right? So because of this, this is another type of non-removable discontinuity.
So now let's look at this example and try to identify any discontinuities that may be present in this function g of x. So we're given g of x is equal to x squared minus 8x plus 12 divided by x squared plus 3x minus 10. So how do we know if there are any discontinuities? Well, firstly, if we're looking at a function and we have something set up with, this sort of fraction, that's kind of an indicator that there may be some discontinuities, as that's often where a discontinuity may be present. And so when exactly do we have discontinuities? Well, you're going to have a discontinuity when the denominator is equal to 0. So if you have a denominator that equals 0, then there is a discontinuity. So how do we know when this function's denominator will be equal to 0? An easy way to do that is if we simply factor it down, right? If we factor the numerator and denominator of this function, it may be easier to identify at what points we will have, the zeros of the denominator. So if we want to factor out the numerator, right? First, again, this is something that you guys should be familiar with from pre-calculus, algebra, and your earlier math classes, but just as a quick refresher, we're going to try to find the places or find two numbers here that multiply to positive 12 and add up to negative 8. So that here then will just be x minus 2 and x minus 6, because negative 6 times negative 2 gives you this positive 12, and negative 2 plus negative 6 gives you the negative 8. So this is going to be our factored numerator. And now we'll do the same thing for the denominator. So take a minute to figure out what multiplies to negative 10 and adds to positive 3. So your answer then is going to be x minus 2 and x plus 5. Again, positive 5 times negative 2 is negative 10, and 5 minus 2 gives you your positive 3 over there. So this is going to be our factored out function. So now looking at this, when will our denominator be equal to 0? Well, simply, we can see that if our x is equal to 2, our denominator would be 0, right? We plug in a value of 2 for x into the denominator, this would be 0, and this would be 7. And 0 times 7 still gives you 0. You also have a denominator of 0 when your x is equal to negative 5, right? If you plug in negative 5 here, that gives you negative 7. And over here, negative 5 will give you a 0. So negative 7 times 0 is still equal to 0. So the 2 points when our denominator will be 0 is when x is equal to 2 and x equals negative 5. So those are the two places where our function will become discontinuous, or will no longer be continuous. And so what type of discontinuities are these though, right? We looked at 3 types earlier. We looked at a hole, we looked at vertical asymptotes, and we looked at jump discontinuities. So what are these an example of? Well, if you're able to cancel out the factors like this, you're able to cancel out the discontinuity, well, that means that is going to be a hole discontinuity. So our x equals 2 will be a hole discontinuity. And then that means our x minus 5 is just going to be a vertical asymptote. And again, if you remember, our x equals 2, this hole is a type of removable discontinuity, where this is non-removable. All right. Now let's look at another example. Okay, now looking at this one, we're given a function f of x, and we're told that it's equal to x squared minus 9 divided by x squared minus 5x plus 6. So what I want you to do now is take a minute and pause the video and try to find all of the discontinuities of this function f of x. I want you to classify, as well as once you've identified these discontinuities, try to classify them, again, whether it's a hole or a vertical asymptote, and if there are any hole discontinuities, Also try to find the coordinates of those holes. All right. I'm assuming that you've attempted to solve these on your own, and now we can look at the solution together. So just as before, we need to identify firstly where our denominator is going to be equal to 0, right? Because that is where we will have any discontinuities. So in order to do that, let's begin by factoring this function. In order to factor the numerator, we can quickly see that this is an example of a differences of squares expression, which means that we can factor it into x plus 3 and x minus 3. Now, this denominator we factor much like we did the other problem. Again, we try to find which numbers multiply to positive 6 and add to negative 5. So that is then going to be x minus 2, x minus 2, and x minus 3. Right? Negative 2 times negative 3 gives you positive 6, and added together gives you negative 5. So this is going to be our factored out function. So now from this, we can identify that we have discontinuities at both when x equals 2 as well as when x equals 3. Right? By substituting either of these numbers in here, we will result in a denominator that's equal to 0. So now how do we identify the types of these discontinuities? Well, firstly, we can see that this x minus 3 is able to cancel out. And since we are able to cancel out this discontinuity here, it is a removable discontinuity and is going to be our whole. So our x equals 3 will be the whole. And now I also mentioned to try to find the coordinates of this. So we'll just do that in a minute. But now we can also then go on to identify the x equals 2 to then be a vertical asymptote. So for this function, we will have a vertical asymptote at x equals 2, which is a non-removable discontinuity, and we'll have a whole at x equals 3. Specifically, if you want to find the coordinates, that's something that I haven't explicitly shown you how to do, but I think it's something you should be able to figure out, right? We're given an x value, and we're also given the function. So a coordinate consists of both an x and a y value. We already know this x over here, and we now need to find the y. Remember, any function, if we plug in the x value, will output the y. So what we want to do then is substitute our x into this function in order to find the y. So that would be giving you 3 squared minus 9 over, again, 3 squared minus 5 times 3 plus 6. So if you want to take a minute and try to evaluate this. So if you evaluate this, you'll see that we get 9 minus 9, which is equal to 0. And you'll also get 3 squared minus 5 times 3 plus 6. That's going to be 9 minus 15 plus 6, which will also give you 0. So what is going wrong here, right? This isn't really making any sense. This is an indeterminate form. Well, that's because we cannot actually substitute our x value into the original function. Rather, what you're going to want to do is you're going to take a look at your factored out one, and you can see we cancel out our x minus 3 and x minus 3, and this gives you what's remaining is going to be x plus 3 divided by x minus 2, and it is this function into which you're going to want to substitute your x equals 3. So if we do so, we end up getting 3 plus 3 divided by 3 minus 2. This is 6 over 1, or 6. And so then our coordinate then for this whole will end up being 3, 6. 3, 6. So this is going to be the coordinate. All right. Now, if we're given a function h of x, that is x plus 1 divided by x to the fourth minus 1, how can we find the discontinuities here, where they're located, what their types are? So if you want to take a minute, pause the video, and try it out yourself, feel free to do so. I will assume that you've attempted this problem, and now let's look at the solution together. So again, just as we've been doing, we need to find a place find the places when the denominator is equal to 0. So just as we've been doing, we need to begin by factoring out this function. We can see that we cannot factor the numerator any further, so it will remain as x plus 1. But x to the fourth minus 1 is actually another example of its differences of squares, right? We can see that this is just going to be then x squared plus 1 times x squared minus 1. So are we done factoring this function then? Actually, no. You can see that this x squared minus 1 is another example of differences of squares. So that means we can further simplify this or further factor this. And that will give us x squared plus 1 times x minus 1 times x plus 1. All right, so this is then going to be our fully factored form. So from this, again, we can identify our discontinuities. We will have one when x is equal to negative 1 and when x is equal to positive 1. You'll notice that our x squared plus 1 is not going to yield any discontinuities here, or we're not something that we're going to be dealing with. And that's simply because if we try to simplify this, right, if we set this expression of x squared plus 1 equal to 0, and we try to solve for x, we get x squared is equal to negative 1. And the square root of a negative number is going to give us an imaginary number. And that's not something that we're going to be dealing with here. So there's no discontinuities that will, or anything we can really get from this x squared plus 1. So our two discontinuities are going to be when x equals negative 1 and x equals positive 1. So now what type of discontinuities are each of these? Well, we can see that our x plus 1 can be canceled out. And so that means that we get a whole at x equals negative 1, and this x equals positive 1 will be our vertical asymptote. So we have a vertical asymptote at x equals 1. This is going to be our answer, or include these here too. All right, now let's try to find the discontinuities for this function, f of x equals tangent of 3x. So you should remember, or you should recall rather, that the tangent function, right, if we have tangent of x, that is simply equal to sine of x over cosine of x. So even though this is not, originally in the form of a fraction, we can simply rewrite this function in this form, sine of 3x over cosine of 3x, in order to make it more approachable here. So when is cosine of 3x equal to 0 is what we're trying to find here, right? And because that's when our denominator will be equal to 0. Well, we should be familiar with the cosine function by now. So if we were simply referencing our unit circle, or if we remember our unit circle, we can figure out the points when cosine of x is equal to 0, right? So we know cosine of x is going to be equal to 0 at the top and at the bottom of the unit circle. So we can say that cosine of x equals 0. Pi equals pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Again, because it is a circle, it's going to keep going over and over again. One other thing I actually forgot to detail here is the fact that we're trying to find the discontinuities between when 0 is less than or equal to, or when x is less than or equal to 0 and 2 pi. So when our x is in between the values of 0 and 2 pi is where we're trying to identify the discontinuities. So again, this would go on infinitely, right? But we're simply trying to find the discontinuities within our given range over here. So how do we know when to stop? Because over here we'll notice that we've already surpassed our 2 pi, our value of 2 pi over here when we were simply looking at if we're trying to find these discontinuities. But the problem is this is not our x, right? Since we're told that we're trying to find cosine of 3x, when is cosine of 3x equal to 0? What we're going to have to then do is multiply each of these values by 1/3, or divide each of these by 3 in order to figure out what those, the discontinuities of 3x is, right? So because we're trying to find what 3x is. So if we have 3x is equal to pi over 2, then our x is going to be equal to pi over 6. So because of that, we're simply going to have to kind of sift through this list and basically identify then within this given range which values of x will result in a discontinuity. So it isn't something that's necessarily difficult, just somewhat tedious. So after going through this list, we can identify our discontinuities as so. So in order to stay within that range, we'll be looking at x is 1/3 times pi over 2, or pi over 6, and so on. So really, in order to stay within this range, you're really just going to have to continue this process for our discontinuities from pi over 2, all the way to 11 pi over 2, right? 11 pi over 2. Oops. 11 pi over 2. So doing so will end up giving us our answers of pi over 6, pi over 2, 5 pi over 6, 7 pi over 6, 3 pi over 2, and 11 pi over 6. And again, we'd see if we continued on to 13 pi over 6, we would now be outside of this range of 2 pi. So that's why we stop here at 11 pi over 6. So these are all going to be our discontinuities. Specifically, these are going to be vertical asymptotes, right? Because we can't cancel this out, so these are not going to be holes, but these are just going to be vertical asymptotes. So that brings us to the end of this video. Hopefully you found this helpful. You'll notice we haven't really looked at any examples of jump discontinuities. That's something that we'll look at in the next video, where we're going to look at a more formal mathematical definition of continuity, and that's going to go hand in hand and be more easier to identify jump discontinuities in that way. So be sure to look out for that video. But in any case, again, please show your support by liking and subscribing, and leave in the comments any questions you may have and what you'd like to see in the next videos. And I'll see you in the next video.